So, first of all, I would like to thank the organizers for having invited me and given the opportunity to present my work, even if, okay, let's have a look. Listening at the talks during these days, I'm feeling a little bit at the boundary of the main flow of this research. So, at least the aim of this talk would be to show how using splines and splines techniques, along with a procedure of matrix compression, we can improve the efficiency of the numerical solution of some partial differential equation. And in particular, my focus has been on 3D Helmholtz problems. This is a joint work with Luca Desiderio, Alessandra Sestini, and a former student of mine that is Alessio D'Inverno. So, before entering into details, just give a brief outline of what I'm going to say. First of all, I would just recall what are boundary element method and their integral formulation. Then we will review briefly the so-called isogeometric setting where the splines came into the game. And then we will see these hierarchical matrix formulation that are used to compress or to compress the dense matrices into sparse ones. And then some numerical example and some development. So, boundary element method can be seen in some applications as a valid alternative to classical domain method to solve numerically partial differential equations, such as finite elements or finite differences method. And the key idea is to reformulate the problem in terms of integral equations that are defined only on the boundary of the computational domain. And so this, of course, implies to be able to solve these integrals in an efficient way. So the main advantages is the reduction of the dimension of the problem, because we are considering the problem only on the boundary of the computational domain. And as a nice feature coming from this is that, for instance, an easier treatment of those problems defined on unbounded domain with bounded boundary. The disadvantages is that in order to construct this integral formulation, we need to know in advance the so-called fundamental solution that is associated with the differential operator that we are going to consider. Moreover, the integral formulation involves some singular kernels, and so you cannot use the standard Gaussian quadrature to numerically solve these integrals. And the last issues with respect to the finite elements or finite differences method is that the matrices that we will arrive to solve at the end of the day will be smaller but fully dense with respect to the sparse matrices that instead we have for the finite element methods. So we are considering an acoustic problem that can be modeled by Helmholtz equations, and we are considering the case where these problems are equipped to be mainly Neumann conditions, where kappa is the wavelength. And these are modeling, for instance, sound scattering or sound vibration. Just to comment that in case we are considering an exterior problem, we need the unknowns should be also satisfy the so-called Sommerfeld radiation conditions. That basically means that when we are going to infinity, the waves should decay towards zero. So, considering the external force null, we can consider a direct integral representation, and so using the integration by part and the second green identity, we can rewrite the equation into this integral equation, where we have this function that is called the fundamental solution came into the game. And for the Helmholtz equation, the fundamental solution have this expression together with its normal derivative. So this is R is given by x minus y, and so x is the source, y is the field, and so this is why in some cases we have some singularity then. So now, considering the trace operation and plugging in the Neumann datum, we will end up with the so-called conventionally boundary integral equation. So it is an integral equation defined only on the boundary of the computational domain. And this is the core of our research. So our method is to solve numerically this equation. Of course, in this way, we will end up the solution only on the boundary. So this is why I prefer to change the name, okay? So this phi, that will be our now unknown, will be the unknown, but just on the boundary. And then, once we have solved this, we can use the representation formula to compute our unknown in any place, in any point of the computational domain. So, isogeometric analysis, so maybe many of you knows or have heard about it, but just to recall for those who are not familiar, this is a new way to deal with partial differential equation. In particular, this was introduced, the name was introduced in 2005 by Tom Hughes. And the idea was we have a computational domain that is coming from some CAD system. And in the finite elements on the finite differences method, what we have to do, we have to mesh the computational domain. And so in this meshing, we have some error, some geometric imperfection. So we introduce some error. And then in this mesh, we construct our finite dimensional space that usually is given in the finite element case by piecewise zero with C0 polynomials. So the idea was to try, first of all, to reduce any geometric error, just using the same representation, so B-spline or NURBS, to represent the computational domain. And then use this very same space also to approximate the solution. And I would like just to underline that, of course, this was not invented by Tom Hughes. So the idea of solving partial differential equation using spline was around also since many years. But I would say that the merit of Tom Hughes is that he belongs to the PDE community. So he was speaking with the same language of the PDE community, and so this was, I would say, more effective. Okay, so instead of speaking about parametrization of computational domain as we do in computer-aided geometric design, he was speaking about push forward and something fancy name for us, but this was exactly the same language of finite elements method. So at the beginning, the isogeometric analysis, so there is a huge work on this new formulation of PDEs, or a new way of dealing with PDEs with isogeometric analysis. But at the beginning was mainly confined in the finite element as an improvement of the finite element setting, but also in the boundary element methods we can have some improvement, and even more, because when we are dealing with 3D problems, we have, let's say, an additional difficulties, because usually the CAD system is giving the computational domain through the so-called boundary representation. So we have only the boundary of our volume. And so in order to set up some finite elements method, you have to construct the volumetric mesh that is not given. In this case, as we are dealing only, or we are working only on the boundary of the computational domain, we can use directly the representation given by the VREP. And so let's say that at the beginning I enter into this field especially with the aim of constructing suitable quadrature rules, because in the quadrature rules, as we are working, we are discretizing also with B-spline, we can make profit of the fact that we are using B-spline. And so using some techniques like spline products or was interpolation, we can indeed, and we have indeed constructed some quadrature rules that are able to solve also weakly singular and hypersingular integrals with a very good efficiency. So, when we have complex computational domains, usually the strategy is to use a multi-patch strategy. Okay, maybe some of you can smile, okay, these are not so complex, but this is just to give an idea, these are benchmark, and also because this 6-patch representation of the sphere avoid any singular parametrization. Okay, sometimes you see these like quarters, but in this way you have some singularities, and even if engineers try to not speak about these points, in these points you have a singular parametrization, and this will affect also the accuracy of the solution. And so what we have a collection of patches that can be glued together with C0 or also C-1 for boundary element method, while in the inner part they are represented by smooth geometries. For instance, in the general setting, just to please engineers, we can use NURBS with positive weights. And these are tensor products patches, so this is another big difference between finite elements and the beginning of isogeometric analysis, because usually at the beginning was just thought as a tensor product topology, even if now the research, maybe I think, I don't know if Hendrik is speaking a little bit, but is to plug in this setting also splines defined over triangulations. This is another challenge. But in our case, we are confined ourselves to the tensor product topology. And so these B are tensor product B-splines. So this is for the geometry. Now for the discretization of our solution, we are using a spline space. And of course, okay, this is just because this spline space we can define on the computational domain, and this can be obtained as a spline space, a classical spline space, bivariate spline space, defined over parametric, let's say, unit square. And then through the composition with the inverse of the geometric mapping, we map back to the computational domain. So our solution on the boundary will be expressed in terms, okay, for any patch we can glue together in terms of these bivariate B-splines. So setting the problem in parametric domain, we will end up with a linear system whose elements are given by this expression. So we discretize just considering collocation. So we just discretize and put a set of discrete points that are here with Si. And these are the right-hand side entries. So as I told you, we have an efficient way to numerically approximate these integrals. So just to summarize briefly the pipeline of the method. So we have first the computational domain that can be represented as in a multi-patch fashion by tensor products B-spline or NURBS. And we are using, okay, we have used, by simplicity, we can consider, okay, globally we have G2 continuity. So it means that even if parametrically we don't have the C continuity, we can have that, for instance, the sphere is G2. So we have a common tangent plane, and also the torus is the same. We have also used the most straightforward way is to use conforming patches. That means that they have the same parameter nodes on the interface. But we have also, is a little bit technical, but we can also use non-conforming patches. Then, in order to construct the linear system, we have seen we have to consider good or let's say suitable quadrature rules, but the problem is that at the end we have a dense and if you are using collocation not even symmetric linear system. And so this is a limitation that IgA-BEM, that is the boundary element method within the isogeometric analysis, share with the standard BEM. Okay, so this the fact that we have these dense matrices, and so if we want to improve accuracy, this means that we have to use a finer meshes, and this means that the dimension of the matrices are increasing, and of course if the matrices are dense, they are expensive, both for the computational cost and also for handling, for the solution. So already at the, I think the around 80s, there was some research on acceleration technique, so the way to reduce, let's say, the dimension of these matrices. The most famous technique is surely given by the fast multiple method, but the fast multiple method is a very efficient method, but is based on the good knowledge of the fundamental solution. So you should know the fundamental solution, and especially this degenerate expansion, in order to build the matrix. And so, for instance, for Helmholtz problem, you have different matrices for different wavelengths. Another I did not mention, but another proposal was using uniform meshes and usually use the wavelet transform. So we have wavelet BEM, and also they gave nice results, but the uniformity is a little bit like a limitation. So we are using instead the third possibility is that is given by the use of hierarchical matrices. And this is a technology that has been introduced by Hackbush just to reduce or to produce a sparse data representation of a dense matrix. So, how there is the main steps of these hierarchical matrices? First of all, we have to make a clustering of the degrees of freedom. And so, in our case, we have to construct a binary trees, and so for recall that in our case, the rows correspond to collocation points, and the columns correspond to our B-spline or B-spline support. So the clustering is done especially just by geometric consideration. Okay, so we put together some reference point, and then we dyadic split these points until we arrive to sets that are composed by a number of points that we established. In this case is the number of leaves of the binary trees. And so we have, for each patch, we have to do two binary trees, one for that clustering the indices on the rows, and one that is clustering the indices of the column. So in total, in our case, we have 2m, because m are the number of the patches. And then we can repeat this clustering on the matrix. Okay, so we have a block that is can be associated by two clusters, so where sigma is a cluster of rows and tau is a cluster of sigma. And so, and also in this way, we proceed just subdividing the matrix into different blocks. But each block is examined to see whether the blocks can be considered admissible or not. And what does it mean, admissible? That it can have a low rank representation. So just to detect which blocks can have this low rank representation, we are giving the so-called admissibility condition that is depending on this parameter eta. But basically what we, roughly speaking, these two blocks are admissible if they are sufficiently distant from each other. And so at the end we have three kinds of blocks. So they are leaves, that they are low rank or full rank, and non-leaves, so the part that should be still refined. So just to consider, so the pink one are the low rank, and so of course sorry, the full rank, and of course the full rank is on the diagonal, because of course we compare the points with themselves, and so they cannot be distant. Okay, so so this is the part that is always we have always in the sparsity of the matrix, but this is the pattern. And what is nice is that this pattern is just given by the geometry of the computational domain, because we have just done this consideration, this geometry consideration. So regarding the low rank representation, okay, we can prove, and this was the work of Bebendorf and also of Chayat, Desiderio, Charlet, is that the possibility of approximating low rank, thinking now about the element of the matrices, is that the fundamental solution does have a degenerate expansion. That this was the property that was exploited in the fast multiple method. And we can see that in the case, so that means that we can rewrite the fundamental solution in this way with this residual that is has to tend to 0. And for the Helmholtz kernel, it can be proved that with the admissibility condition that we have considered to make the block cluster tree, we can upper bound the residuum in this way. And so when this quantity is small, we indeed have a viable upper bound. And also this gives us the guarantee that the low rank approximation could be an efficient technique, could be done, I would say. Because, okay, I did not enter into detail, but this is related with the asymptotically smooth property of the fundamental solution. And for the Helmholtz problem, from the Helmholtz fundamental solution, it is not asymptotically smooth, unless k is equal to 0, so when the fundamental solution coincides with the Laplace. So, okay, but these are technically. So, just to see briefly how we can compute this low rank approximation, of course, we would like to have this, for instance, let's say this block, and we would like, this is an admissible block, and we would like to approximate with a low rank approximation. And this means that this is equal to a matrix that is given by the product of two matrices that have that are of rank R and a residuum. And of course, the idea is to, yes, 10 minutes, to let's say stop when the residuum is less of a certain threshold. So in order to compute the product, the matrices that realize the low rank approximation, the best would be, of course, to use the truncated singular value decomposition. But that means that we need to compute these entries, and we do not want to have it, because otherwise, and so in order to do this, we prefer to use another technique that is called with adductive cross approximation, that is based on the idea that any matrix of rank 1 is, can be seen as the sum of R matrices of rank 1. Any matrices of rank R. Okay, so maybe I mixed it. And so in this way, the approximation can be done iteratively. So we start from a matrix and we add in an iterative way rank 1 matrices till a certain threshold parameter is satisfied. So just a few examples. So the first example is the rigid scattering over a sphere. So we're supposed to have a sphere, and the sphere is hit with a plane wave, and as the sphere is hard, the plane wave produces a scattering on over at the exteriors of the sphere, and the pressure, the scattered pressure, satisfies the Helmholtz equation. This is a benchmark because for this problem we know the exact solution that is given by this, and so we can compute the exact error. So these are the parameters that we have used. So okay, we consider the wavelet 1, that means low frequency. These are the dimension of the bounding box, and this is the admissibility condition. Of course, if we consider eta too small, means that we don't compress too much. If we consider too much, of course we compress a lot, but we are losing accuracy. So of course we have to find eta as big as possible, but without losing accuracy. So we have tested. So this is done by in an empirical way. And so we see here the memory saving, that of course, and this is reasonable, so the saving is especially when the dimension is increasing, otherwise is. And okay, I forgot to mention that at the end, when we have this sparse system, we use an iterative solver. So the solution is done by an iterative solver, and for instance, we have used a variant of the GMRES that is suited by these, the H matrices. So this is the real part of the approximate solution, and this is the imaginary part. This is our low frequencies. This is indeed these are high frequencies. So of course the solution are waving, but still we have very good. And I forgot to mention, in our case, the solution is approximated by tensor product quadratic B-splines, and we retrieve the approximation order expected with quadratic B-splines. So this is instead a reconstructed field outside. Of course, we have taken a disk, and then we have reconstructed the scattered pressure on the disk on the equator. This is the second test problem. So this is an interior problem, an acoustic interior problem on a torus. In this case, the Neumann condition is set such that the solution is this. So again, we have a benchmark. The solution this time is real. And so here we have the approximate solution on the boundary for k equal to 1, and this is for k equal to 3. And here we have the absolute error. And again, okay, the error is the L2 error, I forgot to mention. Here we have either the memory saving for constructing the matrix, and the second column is for the memory saving to construct the right-hand side, because in the sound scattering we have a homogeneous condition, so we didn't have problem. Okay, so just to conclude, very briefly, I show you how we can solve 3D Helmholtz problems using the boundary element methods within the isogeometric setting. And this method can be improved or can be made more efficient just using the technique of hierarchical matrices. So future work is to consider what is going on for very high frequencies. These are challenging problems because we have ice oscillating kernels. Things are getting more difficult. And also currently we are also exploiting or trying to set the problem into a parallel computation, because of course if we have the patches, and the patches can be handled separately each from each other, one from each other. And then, of course, if you have a C0, you can glue together more more, because if you are considering C-1, you have more degrees of freedom than necessary, and then you have to reduce, okay? But this can be done later. And so you can do this parallel computation and also to move to other problems. Okay, so thank you for your attention. And as Lucia, I'm involved as well in the organization and to the SMART conference, so just save the date for the SMART. Okay, thank you.
It seems really nice.
We hope so.
Thank you, Maria, for this very nice presentation. Is there a question in the room? Yes?
Thank you. Did you mention that in the example that you show, you used quadratic B-splines?
Yeah.
Do you have any result or, I don't know,
yes.
thinking about the possible influence of the degree in the structure that you are using?
Yes, sure. But we have started by quadratic, but we have also we tested with cubic and degree 4. But just because we wanted to stress the gain with the hierarchical matrices. And for these problems, if you are using degree 4, you are hitting immediately the accuracy that we have. Okay, because just to let you. So for instance here, you are arriving here with the degree to the -7. And so these are almost at the boundary of your, let's say, parameter. When you are using degree 3 or degree 4, you are hitting these, the error is going more rapidly till, let's say, to the -8. And so the gain in this case of hierarchical matrices is lost, because this is with a modest size of matrix. So maybe with the high oscillating kernels, we can have more benefit of using also higher degree. Yes.
Okay. Is there any other question? Okay. Probably a very naive question, because it's very far from my expertise. But how important is the multi-patch decomposition? Your multi-patch geometry?
Yeah.
It's fixed.
Yes. Okay. We do in advanced.
Yes.
Yes.
Okay. And if you change it, change everything, or?
Yes.
Yes. So it's important.
Yes, it's important. Yes. Yes, we have tried also with to couple with the so-called unstructured B-splines, but in that case, the geometries were changing, and so this was not suitable for this application. No. Okay. Of course, you have to recompute the. Yeah.
Okay. So thanks again.